Hi there. In this tutorial, we want to walk through the WaveNet implementation in Pytorch. And as you can see, the WaveNet is introduced by DeepMind in 2016, the time that there was no attention and transformers introduced. And the WaveNet came when they planned to replace something with LSTM because of some problem with the recurrent neural network, like gated recurrent unit, GRU, or the LSTM. And the problem was, if you suppose that we have these inputs like input number 1, 2, 3, 2, I guess 16. So we can apply each of them to LSTM. And if we say this is one LSTM cell, this is another LSTM cell, so we apply the signal or a sample of a signal here, and it calculates some latent features and send it to the near cell. And the information from these two cells, one is this one is this one, is coming to this cell and it's going forward. We have some sort of recurrence information between time samples. But the problem was we have a vanishing gradient. So the effect of this cell on this cell is somehow vanished. And in some signals, for example, if we suppose an ECG signal and suppose that we want to predict the next component, and the next component we know that should be a P signal if you don't have a T, and it should be related to these parts, which is far away. And usually LSTM look at the nearest neighbors, like the LSTM look at these parts more. And when we go further, the gradient vanish happen and we don't have much information. Some methods came to introduce the skipping connection, like I will skip this to this point, I will skip this to this point. And they were increasing the computational cost. LSTM was slow and it became slower when they have all the connections, and they can be bi-directional, means that not only we get the information from this way, we can get the information from another way. And yeah, those complex architectures came along for processing a sequence. But the WaveNet has a smart view to solving this problem, not by using the recurrent neural network, but just by using the convolutional layers to do a sequence processing. So what they are proposing is create autoregressive model. And autoregressive models means that we want to solve this problem that we have sample from time 1 to time t-1 and want to predict the next sample. We can extend that, like after we predict the next sample, we put it to the system again and we predict the next sample. That can be continued forever. The way that they are proposing a way is using the causal convolutional layers and dilation. Causal term coming from the signal processing means that we don't have any information about the future of a signal. So we only process the previous samples. And so we get the sample of these 2 points, apply a convolution or applies whatever we want to do. And if you look at the last output, which is the next sequence, it get the information from last 4 sample. And if you want to extend that, there are 2 ways, like increasing number of layers. So if you have more layers, it can get like from 6 input samples or from 7 input samples. But increasing layers is not a good idea always, because we are increasing the complexity. And they introduce another way is a dilated causal convolution layers, which means that we use a dilation factor in convolution and we ignore some points in the middle. So for example, if I use dilation 2, it means that I am applying convolution, but not on these 2, but I ignore the middle points and I apply it on these 2. So in that case, I'm for predicting this output, I am using the information from all 16 inputs here. The way that they assign dilation is they double for every layer up to a limit and then repeat it. So it is like 1 to 4 to 512, and again, they have a larger receptive field. They call it receptive field in the paper. So the receptive field can be increased. This is the visualization of a stack of dilated causal convolution layer. And if we go further, we see the figure 4, which is the whole architecture, the entire architecture of the WaveNet. So we have input and we apply a causal convolution on it. These stacks here, you see there are some pages stacked together. They are figure 3. So the way that we define each circle here, each layer here, is defined in figure 4 like this. So we get an input, we apply the dilated convolution on it, and we apply a tangent hyperbolic activation, sigmoid activation. We multiplied them together and applied another convolution layer with kernel size 1. And after that, we have two output. One output is coming from these residual points, and one is the skip connection. So the convolution layer here, it can be two different convolution, not just one. So we have two convolution with size 1, one for creating a skip connection, one for going to the next layer. So the skip connection here is like somehow we get the information from this channel, we get the information from this channel, we can apply like max pooling or something like that for getting the information from each skip connection. We can get the information from different layers to avoid the vanishing gradient. So what we wanna implement is this part. The main part is the stack of residual network here. And after that, we should get the skip connection and apply a ReLU function and apply a 1-by-1 convolution layer. Again, another ReLU to get the softmax and get the output, which is the output here, the last sample, the output here, or this one, the XT. So let's see some of the usage of WaveNet. So they said that they can use the WaveNet for multi-speaker speech generation, for text to speech. So we have a text and we want to convert it to a speech, and it can be vice versa. We have a speech, we want to convert it to the text. And for converting two signals together, like suppose we have a ECG signal and we get the PPG, or converting maternal ECG to fetal ECG, or another example is like converting the T1 weighted images in MRI to T2 weighted and vice versa. But as I said, this is a little old in 2016 because there are lots of advanced methods like transformers and different kinds of transformers emerged after 2017, and they can get better accuracy than WaveNet, but still WaveNet worth to look at. So they said also they can be used for text-to-speech and for music generation. Also for blind source separation, they can use signal classification, like the gesture detection from the EMG signal. Let's dive into the implementation. So I have created an empty project called WaveNet, and I will create a class here, name of WaveNet. And the first thing we want to create is, based on the block diagram, is the causal convolution. And because we have dilation implemented in Pytorch, we can create a causal dilated convolution. And if you want to make dilation, we can passing a value to it. If we don't want to dilate it, we can pass 1. So we can create a class that's cover dilated convolution and causal convolution. I will create a causal dilated convolution, and it should inherit from NN module. I import from Torch. I will create the init method, and I will define the forward method. We have conv1d. We can create convolutional one dimension in Torch, and it get the number of input channels. So I can say in channels, out channels, and I pass these two variables to the class. So these are parameters that we need for creating a causal dilated convolution. And we need a kernel size. We pass that to stride is 1. I suppose that there is no padding. because it makes it a little more complicated. And dilation is something that we can pass to the system. And I say bias is equal to false. I don't want to bias. Yeah, so we need to pass the kernel size and dilation. What's the difference between the causal convolution and convolution that we have defined here? I have prepared some shapes. The standard convolution is like this. So for this example, that kernel size is 3, how many samples we want to remove from output to have the causal convolution? It's probably 2, because we don't want to have the result of convolution on these 2. It means that subtract 1 from it to calculate how many output should be ignored. And if we have dilation, dilation should be multiplied. So it means that if I want to calculate ignore outputs, ignore out index, I can call it. So it is the kernel size minus 1 multiplied by dilation. And for calculating the result, I can say return the convolution on the signal, but I want to get from first to minus ignore out index. Okay, so it means that we ignore some of the last samples that calculated by the convolution. So far, if we back to the diagram, we have created this part. And we want to create a residual block. So the residual block is created by a dilated convolution, a tangent, hyperbolic, and sigmoid activation multiplied, and another one-dimensional convolution. So let's back to the code and let's create res block. Let's create a class called WaveNet. We get a signal and we want to apply a causal in the first step. We want to apply the causal convolution. We don't want to have any dilation. So I initialize self causal dilated convolution one-dimensional, and I use this class, but we need number of inputs, number of outputs. So everything come here, number of input channel, number of output channels. So, and what else we need to is dilation. So we use all parameters here. But about the dilation, I want to create causal conv. That's why I do not pass any dilation. I say dilation is 1. Yeah. And same, we want to create dilated. And in this case, we need to pass a dilation. But as the paper said, we need to have different kind of dilations. We suppose that each stacks have same number of layers. So we need to pass number of stack size and layer size. Based on that, we need to create a function. We say build dilations. So build dilation get stack size and layer size. So the paper said that suppose this is a stack 1, the dilation in each layer, suppose it has like 5 layers, it should be 1, 2, 4 in power of 2. So 8, 16, and until 512. Here I want to say for stack in range stack size, and also for layer in range layer size. So I want to create dilations, and dilations can create it by 2 in power of layer. So for each stack, I can have a dilation. That's better. And I can say dilation for all stacks. Okay. And here, after we finish the loop, append this dilation, return dilation. Using NumPy, I can import NumPy. So I can say import NumPy as NP, and I can say NP vectorize that function that is build dilation vectorized, and I can use that build dilation by just passing the kernel size and stack size. This is function with dilation. I just remove the S. So we have a NumPy array here, and I have to return dilation for all stacks here. And we're supposing that we are not exceeding the number of layers. Otherwise, we have to take care of to start from 1 again after like 10 layers. So we just suppose that the size of the network is not that big. Now we have dilations, so we can create different causal dilated convolution layer for each stacks and for each layers. Let's back to the residual block. So we have this dilated convolution in the residual block. Okay, and we need to pass again number of input channel, number of output channel, the kernel size, and the dilation. This is just one dilation. And after we have that, we need define two activation functions. So I use tangent hyperbolic, and also we need sigmoid. We need also two convolutional layer, one for this residual and one for a skip connection. So we will create these two. So the kernel size here is 1. So first thing we need to say, I want a causal convolution. Okay, and I want to apply it on X and get the result back. And I want to apply two activation function. One is tangent hyperbolic. I call it X1. And another is the sigmoid. Okay, and call it X2. And I want to multiply these two, X1 and X2 together. And after that, they need to pass from a residual connection. So I may call them X again. As we said, we need a residual convolution layer. So just to not remove the input, so I change the name of the input. You can say this is input X, and we have input X here, and we have X, and we can sum input X and X and put it in X again. So we have, this is a residual output. Maybe I can call it res output. Also, we need to apply the skip connection. So the self skip convolution 1D should be applied on X, and this is a skip output. So we have implemented these parts. We have all the skip connections and the residuals. And we need to return both. We need to return the residual outputs and the skip outputs. So one of the things that we forgot is, so here we have residual block, but output size of the skip maybe is different than the output of the residual. So it's better to have a different output for that. We can say this is a skip channels, how many channels we have. And here we can use the skip channels. The residual outputs come again to the input. So it means for this block, which is the residual block, the input and output has same shape. So we don't need to pass two different things. And instead of having two things, we can say just residual channel because we have a skip channel there. So you can remove this part and I just say residual channel, which is here, and also it's coming here, and it's for residual convolution. The output also is the same. And for the first causal convolution, we have again. So we're just making it a little simpler. So we have residual channel coming for skip connection for input and output of residual block. And we need a stack of residual block. And a stack of residual block, here you'll see that we have created once and we have to create them in K layers. So for creating that stack, it's a better idea to not have information here, but create another class, a module called a stack residual blocks. So in a stack of residual, what we need to get from the WaveNet so far is the layer size and the stack size. I think that I can put the build dilation And instead of they're here, and I can say build dilation function, and I can do the vectorization here. I'm just moving everything from that part to here. So I can initialize the residual block, and what it's need is the residual channel. So that's why I need pass a residual channel here, and also the skip connection and kernel size. Okay, and here we put everything there from the residual connection to kernel size. I can make it more simpler because this is like a stack one, and we have another stack, and we don't need to put them in different array. This is just for making it more clear. So in other words, for each dilation per stack, and I can say for dilation in per stack. So if I do something like that, I can create a residual block. And what else we need to pass here is dilation. So we can pass a dilation here. And this is one of the residual blocks. So I can create residual blocks. And for making it accessible for all, set it as a class parameter. So what we are doing here is we are creating a stack. We're just putting them in a list. And then we want to apply it. So we have an output, the residual output coming here, another residual output coming here. And it's start from 1 to 512. Yeah. And again, start from 1 and 512 and so on. So let's back to what we were doing. So we have residual blocks and we want to do the forward function. For residual block in self res blocks, and we get two output because this is a residual block. One is the output and another is the skip connection. But the first residual output is X. This is more clear when we want to see what's output of this. And also we need to stack the skip connection. So we can say skip outputs, and we add them to a list. And what we want to return from this is the residual output and the skip output, but we want to have a stack of skip outputs. Okay, so this is a stack of tensors. We can go here and create a stack of residual block, and we name it a stack residual block. The input is the stack size. So we get it from the input. We want to get the layer size, the residual channels, which is as input channel, and the skip channel, number of skip channel. So we need pass and a skip channel, how many skip channels we want. And we have the kernel size. The skip channel coming here and apply on the one-dimensional convolution. So the output size is equal to the skip connections, the skip channel. So that's why I can say the skip channel and output are same. So from this figure, you can see that there is a causal convolution and there is a layer here. I call it like a dense layer. So let's create that dense layer. I want to create it here. So a class dense layer. So here we are getting the skip connection. We are getting the skip connection. And what we want to do with this skip connection is using the torch sum to add skip connections together. Our assumption is the skip connection that we are passing to the system is created of number of batches, the number of channels, and the number of time samples. But because usually we have number of channels in the last, so we have number of time samples here, or samples here, number of channels here. So I want to reduce it over which dimension? I want to reduce it on dimension 2, okay? And I want to get the output here. And we want to define the ReLU. And what else we need? We need to define a convolution, and we need to have the input channel and output channel. And I know that the output channels, it's not important for us. We have on the input channel, we can pass only the input channel. And the kernel size is 1. And dilation, we don't have any dilation, bias is false. Now I can remember which is not right, is this one and this one. That we don't want to have a causal convolution there. That's why instead of causal convolution, maybe it's better for these two, I change them. After the output, we need to pass it from ReLU and the convolution, another ReLU and convolution. So it would be self.ReLU out and self dot, this is another out, and we will have self dot convolution, and we get the out. So we want to do it twice, so I can say for I in range 2, do this. So this will be applied twice, and what else? We will have a softmax and the output. So I can say out dot softmax, and we can return it back. And instead of having this function, maybe it's better to have like ReLU. We have self dot softmax and nn dot softmax with big S, and here I can pass a dimension on T, so that's why I select dimension 1. Here, instead of that, we can say return the self softmax after applying the out. Okay. So we have the dense layer. So we can use this dense layer, initialize it, and the dense layer get the number of input channels, which is equal to number of out channels here. Okay, what else we need? So we have everything. So we only need the causal convolution. So I can define the causal convolution. We have a definition here, causal convolution, and we don't want to have a dilation. So it would be causal convolution, and the input channel and the output channel of that, it's equal to the input channel, and we don't have any dilation, as I said. Yes, and let's finish the whole process. So first we apply the causal convolution on X, and we get another X. Then we apply a stack of stack residual block, and we apply X to it, and we will return 2 things: the residual output and the torch stack for skip connections. We don't need the residual outputs because we are using the skip connection. We have the last layer here from the last residual connection, so we don't need it. But if we need it, we can use it for something else, like predicting 2 different things in the same time. After that, I have dense layer, which get the skip connections and return the output to me. So it seems that we have implemented everything, and it's time to test it. Here we can create a new test and go to the project folder and create another folder called the tests, and hit the OK and create test WaveNet. So we have test WaveNet. First, we want to call the WaveNet just by some random values and see if we return something back, and we can have a real example then. For this purpose, I only need the WaveNet. So I just call WaveNet and WaveNet was uppercase. And what we need for WaveNet is number of input channels. So I can say my input channels 1. I don't need to define itself because everything can be defined here. So I only have input channels and I need output channels. How many channels we have in output? So we have output channels, I think maybe 1. So we are converting one channel to another channel. What else? We need a kernel size. I suppose that kernel size maybe, just for example, it can be 3. And what is the stack size? A stack size, you remember that it's how many stacks we put together. I just set 2, and how many layers we have. I just set it to like 5. Okay. So we have our wavenets, and I can run test, run wavenet, just to see that it is working or not. So we need wavenet, and we need pass an input. So we need an input. What is input? The input can be defined using the parameters in Pytorch. So I can say from torch import nn, and here we need nn dot parameter. I can use import numpy as np. I can use np dot random, and the size is, I set the number of channel, the input channel, and how many items is in that signal. So I'm supposing that I have a Windows, like I'm not feeding a whole long signal. I'm just feeding like 200 samples maybe. So sample size is like 200. It can be more like 2000. So I am using a 2000. So this is my input. But we need to make a batch. So what is a batch size? Batch size is, suppose the batch size is 8. And for that, repeating, I can use from inops. I can import repeat. So I can say repeat the self input. I want to say we have number of channel, number of time, sample size, and we want to change it to number of batch, number of channel, number of time. Yeah, and we need B, which is the batch size. Okay, that's it. And we need to assign it to self input. Everything should be okay. This is our output. And if I just want to see the output, I'm not sure that we will get the correct result. But one of the other things is here, we say number of channel, number of T, but it's not right. So usually we should have vice versa. We should have number of sample size, and after that number of channels. That's why we'll change these two for readability. This is exactly the same thing that we discussed it here, that we need sample with batch size, time, and number of channels. So let's run this. Data position 2 must be tensor, not numpy array. So here I can say torch. I can import torch rand n. So let's see. What is the error? It said given groups, weight of size 1 by 1 by 3 expected input, this size to have one channel, but got 2000 channels instead. So it means that the convolution is supposing that the channels is here in Pytorch. We need to have a number of channels in the middle. So we have number of times here, number of channels in first. We have something like this. So we need to change the WaveNet because what we were supposing is different. We are getting the C and after that the T. So when we want to do a skip connection, we have to run it on channels, and when we want to do softmax, we need to apply it on dimension 2. I'm not sure about these two parameters still. So it said that got 3 dimension, expected 4 dimension input for 4 dimensional weights. So because we have dilation here and we are, this size is same, we have a dilation here. And when we want to add this signal to the signal, and because this is causal, we are removing some of the part of the we're removing some of the part of the residual output because of causality, and we have to do the same for input. But for input, we are more interested to the latest samples. It is not in the future, but it is in the current step. So we ignore some of the sample from the first just to solve this issue. So this is one of the things that we have to take care about. We can write something here like calculate. In the paper, it didn't mention it as field of view, it said receptive field. So we can say receptive field, okay? And it needs the stack size and layer size. So we have stack size. So we have for each layer in layer size. So we are doing this, okay? So this is the dilation of each layer. But when we have a stack size, so we are multiplying the receptive fields by the stack size. So if I apply mp.sum on it, I'm calculating the receptive field. So why I'm doing that? Because I can create another test, calculate receptive field. So when I want to calculate receptive fields, it means that I want to have a self WaveNet. They can have a stack size as a parameter, and self.layer size is equal to layer size. And here, when I want to pass them, I can pass the stack size and pass the layer size, okay? And here also, I don't need to pass them to a function. I can say this is a layer size and this is a stack size, okay? In that case, if I want to show you the receptive field of this network, you can say self.wavenet calculate receptive field and print it. I just want to print it. It's not the unit test. I just want to show you so it said it is 62. So with 2 stack and layer size 5, the receptive field is 62. So we can also calculate the output size. So we can say calculate output size. And output size, if we get an input and we know the receptive fields, we can calculate it easily. So we can say x.size 2 minus the self-calculate receptive fields is the output size. So it is output size. And just to be sure that this is not a fallout, so we do something like that. Yeah, we need to do same thing, but we apply it to input. So we can say skip output is skip output and this. But difference here is we need to have the same size, and every time it's changing the size. So we need to say, what is the skip size we want to pick? And we can pass that skip size to the input here. We can say, what is the skip size? And every time we just get the latest of the skip size. And it means that when we want to run the residual block in forward function here, we need to pass the skip size. And that skip size again can come here and go to and come here. That when we want to stack residual block, we want to forward something, we need a skip size. So instead of passing the skip size, one of the things that we can do is we can calculate the output size based on the input. And we say a skip size is equal to output size. So it's exactly the same way that we can keep as much as information that we need. I can do something smaller than a skip size, but I cannot do something bigger than a skip size. So that's the best way that we can do. So another problem that I found is when we want to remove the last ignore out index from the output of the convolution for creating a causal convolution. Let's see the images again. So we have this dilated convolution, and every time it's come here, we are removing some samples because of the dilations. And because we have different value for dilation, the output of each layer has different shape and different lengths. That's why I said we want to have a padding same to have a same output as number of inputs. So the time sample should be the same. In that case, we can use our self-ignore out index. Otherwise, if you don't want to use that, I've seen in a Stack Overflow for causal convolution, they just ignore the last index. And that's okay if you have a kernel size 2 and padding 1. But if you want to have a more general causal convolution, it's better to have this. If you see the figure, it said that here we have dilated convolution. It didn't say about the causal convolution. Instead of causal dilated convolution here, we can have just the dilated convolution. So we can pass like a variable here that do we want to have a causal or not. And if we want to have a causal, so we can return this. Otherwise, we can return everything from the convolution. So these two parts can be changed to make the code works. So in that case, if you run, so you will see that we have the output, and this means that the code is working. And this is just a unit test. We want to train the model on some data and to see if it is converging and everything is fine or not. So I think now it's time to have a real example using real data. And for that, I have opened the Visual Studio Code just to create a Jupyter notebook, and I have a file here, a CSV file, which is included from different times. And there is a signal. This is a physiological signal, and there is open channel, number of open channels. I don't know what is the channel here, but it was in the Kaggle. We have different open channels, like 2 here, 1, 2, 2 here. So what we want to do is we want to create a time series prediction. We want to have these signals, like suppose that we have different time sample of signal. So this is our signal here. Like this is in time t, and this is in time t plus, I don't know, n, okay? And we have our signal as open channel, the last column here. And every time that we have a signal, we have a status of number of open channels. And what we want to do is we want to have like this signal and predict that is this open or not. And then another window, we can have these three, and we can say, is this open or not? Okay. So this can be, so instead of autoregressive, it is somehow a regressive model. So we have these inputs as a time series. They have dependency in time, but we want to predict another signal or another status based on that. Other application is like we have whole sequence here, and based on this sequence here, we want to predict like these two sequences. It can be more than one prediction. It can be multiple prediction because we are doing a sequence to sequence conversion. Okay, let's create a file here and call it demo.ipynt. So the first thing we need to load the data. So you can use pandas. And if you haven't seen pandas series, I recommend you see the series we have provided. And we can use read CSV, and we load the train Kalman filter here. So this is a data frame. And what we want to do is we want to get signal, and also we want to get open channels. And we want to convert these to tensor. But for now, I think the better way is to create a data set and then data loader and use a main loop for training the network. Let's do this. So I will create a class called time series dataset. This dataset should inherit from torch, utils, data, and dataset. So we need a function defined as length, and we want to get the length of datasets. And also we need another function, another method for get item, and that get item get an index. Okay, we have a self here, and also we need init function. We can pass an x and y, which we are supposed they are data frame, so we can say they are pd.data frame, or maybe pd.series. They are series. So we only need these two, and also we need another thing. We need, maybe I can just pass a df to make it more simpler. And what else we need is, so as I said, we have a window. We need to find out what is the sequence length. What is the sliding window length? So I can call it sequence length. And I'm supposing this is like 10. Okay. And what we are going to do here is, when we want to get item, we want to return self dot. So for signal, so we have df here, so we can say self.df is equal to df, and here we can say df. If the data is too big, we have to just pass the path of the data, and here we load it section by section, or in other approach that pandas allow us to load the big data in some chunks. But for this problem, we don't have any issue with that, and we do not bother ourselves to do some advanced loading mechanism. So we need to get the signals, but instead of this, we can say I want to get from which rows, from first column. And for y, I can say something similar, but for second column. So we have data frame loaded, and if you just want to see the df.shape, just showing you, we have about 5 million records. I wanna pass based on the sequence length. When I say give me the index, for example, index 0, I'm saying give me from index to index plus sequence length. So the sequence length should also be a parameter. And I like to have a super in top, and we can have sequence length is equal to sequence length. And here, sequence length can be used here. And for y, we don't want to pass a series like this. We want to just pass one value. And for that case, so let me make it a little more clear. So we have x, and we have y, and for y, we want to get the latest value. The latest value is index plus self.sequence minus 1. Okay, and we want to return x and y. That's it. Now we want to instantiate that data sets. I can do the instantiation here, and because this is a class, I can name it by uppercase. I can name it uppercase, and here I have my class. I can pass df, and I want to say every 1,000, any value can be used here, and we have time series data set. So we have time series loaded. So we have our data set. Now we need to split it to train and test, and create data loader for training and test purposes. For doing that, we can use torch.utils.data. There is a random split. We can use that. It said which data set you want to do a random split, time series data sets, and what are the lengths that you want to split it. Let me show you something. So if I say length of the data sets, we haven't returned any lengths. That's why it's return us a non-type. So the way to return the length is we say return. We need a data frame. So data frame and the first shape, which means number of rows minus sequence length. So if I do it again and run it, so it will return us the length because we have implemented the length method. And here we can use this lens and we say, I wanna 70% of the data to be the train and 30% to be test. So I can say maybe this is cleaner. So I can say train numbers, which is this one. Okay, and here I can say the whole lens minus train numbers. And I can replace this with train numbers too. I can say torch, utils, data, data loader. Okay, and for data loader, we need to pass the data sets. The output here is two things because we have split the data. First is train data set, and second is test data set or validation data set. So for training data sets, we are loading data loader on it, and data loader also need a batch size, and we can do shuffling. The batch size, I said like 8. It can be bigger, but currently I'm not on a GPU. I'm not working on GPU. And next thing I said is the shuffling. So shuffling can be true. Same things for test datasets. And here we can say train data loader, and here test data loader. So we will create a generator for loading our data. If we run this, so it will be run without any issue. Now we can go to our main loop. So we can now load our model. So we have WaveNet, and WaveNet needs number of input channel, which is 1, number of output channel, which is 1, number of kernel size, I suppose it's 3, can be 2 also, and stack size, I suppose it is, like, let's make it smaller, so 1, and layer size is like 3, can be more than that, like 5, and what else? So I just put a out size so we can define what is our out size. Let's look at the code. There are some small changes we've applied. First is here, so we get the out size, and that out size can come here if our out size is bigger than the skip size. The skip size we calculated from the model. If it is bigger, then we can raise an exception that this cannot be happen. We can also show some error message, but if it is not bigger than a skip size, we can use it for a stack residual block. So in that case, we can control the output size. Another change I've done is here. So the input of the model is batch, channel, and T, but there is a point that I forgot to mention here is the dense layer, the final things are, if you see the look diagram, the things that coming to the dense layer is a stack of skip connections. So it is a stack of skip connection because appended, I call it appended stack. We append them, and then we have the batch, then we have the channel, and we have the output size because we cut the skip connections length based on the skip size. So this is the length, and if we have this length and we want to apply sum, we have to apply sum on the appended skip connection. This should be fixed in your code. And also another change is the softmax. So we want to apply softmax not on the batches. After applying this sum, we are removing these appended skip connections. Therefore, we have these size. And when I say 1, it means number of channels. And we want to apply softmax not on the channels, different channels. We want to apply softmax on output size. So this should be 2, okay? These are fixes that we need to take care of. I want to solve this issue using the categorical cross entropy. What do I mean by that is, so we have an output which can be any integer number after softmax, and the number of out size that we have defined here can be like a number of classes that we have. So I'm using the last layer instead of sequence to sequence modeling using as a classifier. But if we don't want to do that, we can just have our skip channels. And after that, we can connect our WaveNet to another linear layer and create a new model called like classifiers based on WaveNet. So we can have different approach. If you want to do that, we want to have the output size here. For that, I can say calculate the max on this column. The max is 10, so we have 10 different number of classes. So here we can use this. And I say, I want to have output size in size 10. The next step, let's define optimization. From Torch, we can use Adam. You can use different like Adam weighted or different algorithm. I just want to use a simple. So on the parameters of the model, I don't want to change default values. And our last function is torch nn dot cross entropy loss. Now we can say number of epochs. I set it to, for now, just for one. And we say for epoch in range epochs. So what we wanna do is load the data loader for train data. So we can say for a step and X data, Y data, I say train data and Y train in train data loader, but I wanna have enumerate on that. And also TQDM, I want to use TQDM to make it tractable for loop. And for that, we can say from TQDM import TQDM. So we have our training data. We need to pass the training data to the WaveNet model. There are some issues I will talk about it because we have here the series, but we want a tensor. But I will talk about it. And this is our output. And we need to say optimizer 0 grad. We want to make the gradient 0. And we calculate the loss using our loss function between our output and Y train. And we say loss should be backward. And after that, optimizer should go one step. So the X train is, as we defined here, and as we define number of batch size, it is like 8 by number of samples. But we need number of channels too, and we have only one channel. That's why we need to unskews X train on skews, and on X train do unskews on the first. The 0 is the batch, the first is the channel. As I said here, 0 is batch, first is channel, and the last is the time. So we need to do that, and we have X train here. Just to be sure that X train is float, not double, we can also say float, okay? We can also show this is epoch. What epoch number can be here? I want to see the loss, so I can say print loss for a step. So here I want to show the loss, which is last item, and here I want to show the step, and this is F. So if I run this, let's see some errors and fix those. Okay, it said batch must contains tensor, numpy arrays, numbers, dictor list, found pandas series. The things that we can do here is we return values. We're moving from pandas to numpy. So let's have a data set again loaded, and let's run this. What else? NumPy in 64 object has no attribute values. So the thing here is the Y is just one number and doesn't need to have values. Do this and run this. So we will have another expected target size 8 by 10, but got 8. Is happening here. We have Y output and Y tray. One of the other things that we need to take care of is the size here. The output size should be maximum plus 1, because suppose if we have 0 and 1 and we say what is the maximum, it is 1. And in that case, we are just setting the size output as 1. which is just one neuron, and the classes were 2. It means that we need 2 neurons, but we only selected 1. So by checking the output size and white range size, we can find out that the first input of the loss function, which is the output of the WaveNet model, should be in size of batches and size of classes. So it is correct. And for white train, we have also, it is not one hot coded, it is just the number of based on the number of items, we have class number, and loss function can handle that. If I run this, so I can just remove these because there's no change. I just unskewed the train data, and after that I skewed the output because we don't need the channels. We don't need the information in the channel. That's why I think we can start training. But for each loop, I don't want to show a result. I can say global step like 100 or maybe 1,000, and every 1,000. So if a step, the mode of a step to global step is equal to 0, I can print the loss. So if I do it, let's stop it again, and I just want to remove these 2 lines too. So it is training. It's in 2.3. The loss is 2.3. The loss is cross entropy loss. We can also add the accuracy. The loss didn't change as you see here, but we should wait until we see any convergence. So the system is training, and still there is no effect on the loss. Another thing we can do is, besides of having the loss, we can have the accuracy, because this is a classification. And for accuracy, we can find the maximum element of the output for each rows. And after that, we can calculate the accuracy. And in that case, we will have accuracy. But still, the model is not practical, and we have to change some parameters and fine tune it to make it work. You can see that accuracy is dropped even for after training.
So now I'm thinking that maybe having limited size of the stack maybe is not a good idea for this problem. And so it's better to get the maximum number of features from the skip connections. But after having a dense layer, I'm thinking that maybe it's better to have a linear layer, because in this problem, we are working on a classification issue. We can create another class like WaveNet classifier like this. So we can say WaveNet classifier. For classification, we are saying that number of input channel, number of output channel, the kernel size, the stack size, layer size, and the output size here. I don't want to use this output size as the output of the model. That's why I can remove these parts. But here we can have a WaveNet classifier. And for WaveNet classifier, we can have output size, okay? And like before, we will put anything here, like the stack size, the layer size, the kernel size. But this time we are creating a WaveNet. So this is a WaveNet. And we know that WaveNet get all these parameters except the last one, the output size. But we also need to have a linear layer. It needs number of input features and number of output features. So the number of input features can also be defined, like based on the WaveNet and based on the input to the WaveNet, we can define the skip connections. So the skip size, calculate output size, this function, which needs the input, and we know the number of output layers, which is this. Okay, and here we just say self dot WaveNet, and we get the X back, and we have our linear layer. And maybe a softmax on the linear layer is good. So let's define a softmax too, self.softmax, and we have an n softmax. And we want to do it on last dimension. And we can say self.softmax on the result and self.linear on X. We can return this as a classifier output. But this should be defined by the WaveNet. So that's why maybe it's better to pass the WaveNet to it instead of having all these parameters. So I don't need a stack size, stuff like that here. I can remove them. And I just need to pass, I don't need a stack size, layer size. I just need to pass WaveNet, this WaveNet, which we know this WaveNet is from class WaveNet. In here, I can say WaveNet, calculate output size. And this WaveNet can go to the WaveNet, and we can say self.wavenet calculate output size X. One of the things we can do is we can get the sequence length. Maybe it's better to be before output size. The sequence length, like this formulation, can be used for calculating the output size of the WaveNet. So if we calculate the receptive fields, yeah, like this, and we have a sequence length, so you're exactly on the right place to calculate the output size of the escape connections. So this should work. So if I use WaveNet classifier, so here I will say WaveNet classifier, WaveNet classifier. And I use this WaveNet classifier whenever I'm using WaveNet, okay? And I'm just passing, if we see what parameters, it needs a WaveNet and sequence length. The sequence length is defined here when we are defining the time series. So I can say sequence length here, which is like 100, I can say maybe 1000. So this is sequence length, can be used for next parameter. And we want to have output size, which is this. We don't have it here anymore. So if I restart the kernel, I have to restart kernel to load everything. Cannot assign module before module init. Oh, I forgot to say super init because this is inheriting from an N module, so I have to use this. Let's do everything again. Okay, now we have a classification based on WaveNet, and let's see how these outputs can change during the iteration. The loss is this one. You see the loss is reduced, and from 0 now we get 37% accuracy. I hope it can be continued if I didn't have any problem. Again, a little improvement in the loss. It's a good sign. We have a wrapper on the WaveNet sequence-to-sequence modeling for classification. We can see that there is a try to decreasing loss, and seems it's working fine. So I made some changes for training loops. So we have the bigger learning rate here, and also you remember that we had the WaveNet outside here. I just bring it back. So we have a WaveNet initialized here, just for having a more cleaner course. So we have just WaveNet classifier. And I also tried the scheduler. So every 500 iteration, I will apply the scheduler exponential LR to the optimizer. And I didn't receive any improvement in performance with the scheduler. That's why I was just put it here to show you that I have tried these and that. Other parts that I have changed is this. So after each 500 iteration, we come here and apply the validation data set on the model. And for that, we use no grad because we don't want to use a gradient descent here. And we apply the model, we apply the data to the model and calculate the accuracy and calculate the average of accuracy for 200 sample of data. The reason I'm just putting this is because my CPU and my GPU has some limitation and data is really big, about 5 million records. So you can remove these parts, and also you can make the bigger batch size here and try different sequence lengths here. And I put this for training. So remember that the loss here is loss for validation. After each 500 epoch, we do a validation. You can see it started from 11 and it is increased for each 500 iteration. I put it a lot on running. So it seems that it can even be improved more, but I stopped it here. This is the way. This is just, I stopped the cell and keyboard interrupt. And you can see that we could get about 74% accuracy. I think we can get more if we let it to be trained for at least one epoch. It is not even one epoch, it is half of an epoch. And you can increase the epoch number here and also change the kernel size, number of stack, and number of layers. Also, one of the things that I've noticed is if we have some sort of normalization layer in between, so we didn't have used any normalization like batch normalization, the layer normalization, I think that would be helpful, because I've seen sometimes the softmax is just showing one value, which means the output of the previous layer is saturated. So for getting better and better performance, we can work with this model. But as you can see, with this data, we could converge the model to like 75%. I don't know the goal of this, but different parameters like the sequence length and the number of batches led it to be trained for more than at least one epoch. And yeah, so thank you for watching this tutorial and have fun.